here's our first lesson in the trig identities and equation unit. In this lesson, I'm going to focus in on a few different types of identities, the cofunction identity, like the title tells you here, but also transformation identities and even odd identities of trig functions as well. Before I get into the lesson, I just want to go over quickly with you what an identity actually is, in case you forget from your last course. So I'm going to write two equations on the screen. Okay, I've written two equations on the screen. One of these equations is a very special type of equation called an identity. Let me show you why the one on the left is what we call an identity. If I tried to solve the equation on the left, I would expand the right side. Notice the left side and the right side are exactly the same. And if I continued the solving process, moved all the variable terms to the left and the constant terms to the right, notice I would get 0 equals 0, which tells me there are an infinite number of solutions to the equation. In fact, I could plug in any real number for x and the original equation would be true. Because if we look at the second line, we see that the left side and the right side are actually the exact same thing. If I plugged 1 in for x, I'd have 12 times 1 plus 4 on the left and 12 times 1 plus 4 on the right. So I'd have 16 equals 16. So 1 is an answer. But I could also plug in 2 for x. 2 would also work. If I plugged in 2 for x, I'd have 28 equals 28, and so on. Plug in any real number for x, and it makes the left side of the equation equal to the right side of the equation. So that's why we say the one on the left is an identity. An identity is an equation that is true for all values of the variable. The equation on the right, however, is not true for all values of the variable. There's only one value of x that makes the left side equal to the right side. And let me show you. If I tried to solve this one, 12x plus 4 equals 6x plus 2, I'll rearrange this. And I get 6x equals negative 2. And I would get x equals negative a third. In fact, that is the only value of x that makes the left side of the equation equal to the right side of the equation. If I plugged in any other value of x, the left side would not equal the right side. So this red equation on the right, we say is not an identity. So now that we know algebraically what an identity is, let me show you graphically what would happen in these two scenarios. Okay, my first equation, the left side was 12x plus 4. So if I were to graph 12x plus 4, it's that line right there. And the right side was 4 times 3x plus 1. If I were to graph that line, notice it went right over top. They're the exact same line. Which is why for any value of x you plug in, you get the exact same value of y. The two lines are exactly the same. But for the equation I did in red, 12x plus 4 equals 2 times 3x plus 1. Let me change this to 2 times 3x plus 1. And notice, let me zoom in. These two lines are only equal at one point, right here, at an x value of negative a third. That's the only time the two lines will give you the same y value. At any other value of x, you would get different y values. Which is why in our solution we found out x equals negative a third is the only value where the left side equals the right side. Okay, so now that you've had a review about what an identity is, let me remind you about some identities you should already be familiar with. You should be familiar with the reciprocal identities, the quotient identities, and the Pythagorean identity. And for each of these identities, when I'm saying they're an identity, I mean for any value of theta you plug in, the left side is equal to the right side. They're always equal to each other. So for example, let me graph sine squared theta plus cos squared theta and show you that that's always equal to 1. There's the graph of sine squared x plus cos squared x. Notice the graph is a horizontal line through 1. It's always equal to 1. No matter what angle I would plug in, no matter what value I plug in for x, I would get 1. For example, I could plug in negative 300. Doesn't matter. I get 1. I could plug in 4007. It's still equal to 1. It doesn't matter what value you plug in for the angle, x, it's equal to 1. Sine squared plus cos squared is always equal to 1. And similarly, tan theta is always equal to sine theta over cos theta. And cosecant theta is always equal to 1 over sine theta. And you can read over those identities there. You should be familiar with those. Here's a table that's just kind of building off of the last one I told you. It's just showing you that, you can square both sides of identities and they are still identities. And if we look at the Pythagorean identity, we can rearrange it to come up with other identities we know are true as well. And then I have a table of general tips for when we're proving identities that will help you prove that the left side and right side are in fact the exact same expression. They're in fact always equal. So we always start by separating into left side, right side, and you cannot cross between sides. So we're not going to be like adding or subtracting things from both sides or dividing both sides by something. We're not going to be moving terms between sides. We're working with the sides completely separately. And then on each side, a good strategy is to try and change anything that is not written in terms of sine or cos, rewrite it in terms of sine or cos using identities that we know. And if we have fractions being added, usually we want to combine them by finding a common denominator. And always be on the lookout for difference of squares, or any way you could use exponent rules that you know. So before we get into the new identities for this course, let's practice proving 3 identities you would have had in your last course. So just so you remember the methodology for proving identities. Step 1 is always to separate into left side, right side. Now, if this is an identity, the left side of this is always equal to the right side of it, which would mean that tan squared x plus 1 should be the exact same graph as secant squared x. And hopefully you notice those 2 graphs went right on top of each other. They're the exact same function. No matter what value of x you plugged in, you'd get the same value of y. So our job here is just to prove that by using other identities we know are true. So one of the main tips that I always give is to try and rewrite anything not in terms of sine and cos to be in terms of sine and cos. So tan squared x, I could use the quotient identity and rewrite tan squared x as sine squared x over cos squared x. And then I have plus 1. And if I follow that same advice, then on the right side, I should change secant squared x based on the reciprocal identity. Secant is the reciprocal of cosine, so I could rewrite that as 1 over cosine squared x. Now that everything's written in terms of sine and cos, I want to look for how else can I manipulate either side so that I can show they're in fact the same thing. On the left side, I have a fraction plus 1, so maybe I want to combine those fractions. So I'm going to rewrite 1 so that it has a common denominator with sine squared x over cos squared x. So I'm going to rewrite that 1 as cos squared x over cos squared x. Right? That's equivalent to 1. And now that they have a common denominator, I can rewrite it as a single fraction over that common denominator. So I could rewrite as sine squared x plus cos squared x over the common denominator, cos squared x. And then the numerator is the Pythagorean identity. Sine squared x plus cos squared x is always equal to 1. So I could replace sine squared x plus cos squared x with 1. So I have 1 over cos squared x, which, if you notice, is the exact same thing we have on the right side. So we've just proved this. We can say left side equals right side. We're finished. So let me just jot down what rules I used here. So I changed tan to sine over cos using what's called the quotient identity. And I changed sine squared plus cos squared to 1 using the Pythagorean identity. And over here, I changed secant squared to 1 over cos squared by doing the reciprocal identity. So if you wanted to add that into your notes, you're more than welcome, but I wouldn't expect you to include that on an evaluation. Let's try another one. Let's start by separating into left side and right side. Now the left side, I don't think there's anything worthwhile doing to the left side. That's already pretty simple. On the right side, notice I have a difference of squares. An a minus b times an a plus b is equal to a squared minus b squared. So it would be equal to 1 squared, which is 1, minus sine squared. So I've got 1 minus sine squared x. And based on the rearranged Pythagorean identity, I know that 1 minus sine squared x, I know that's equal to cos squared x. So that one's done already. Left side equals right side. Part C, let's separate to left side, right side again. Okay, this is the first one where maybe there's no obvious first step to do, but follow along with what my logic is here for how I'm going to prove this identity. On the left, in the numerator, I have a sine squared x. I'm going to rewrite that as 1 minus cos squared x. I know I can do that based on the Pythagorean identity. And the reason I do that is because now in the numerator, I notice I have a difference of squares that if I factor it, I'll be able to reduce with the denominator. Right? In the numerator, that 1, you can think of that as 1 squared, right? 1 squared is equal to 1, so I have a difference of squares. Got a 1 squared minus a cos squared, so that would factor to 1 minus cos x times 1 plus cos x. And now that the numerator has been factored, I can cancel out the entire factor of 1 minus cos x because that exact same factor is in the denominator. And what I have left is just 1 plus cos x, which is exactly what I have on the right side of my equation. So 1 plus cos x is equal to 1 plus cos x, so left side equals right side. I've proven that identity as well. Now, that's not the only way to prove that identity. I'm sure there's lots of ways, but that was the first way I thought of, and I think that's a pretty simple way to do it. Now, the next thing I want to talk about are the transformation identities. These ones are pretty straightforward. You've worked with transforming sine and cos functions a lot up until now, so these ones should be pretty obvious, but let me just show you in Desmos what we're going to figure out. Okay, in Desmos, I have graphed in blue the function cos x and graphed in green the function sine x. Notice they're the exact same function, they've just been horizontally shifted. So for example, if I were to take my blue cosine function and shift it pi over 2 to the right, it would line up perfectly with the sine x function. And let me show you that. Let me transform this cos function pi over 2 to the right. There we go. Notice the cosine function is now exactly in line with the sine function. So if I shift the cosine function pi over 2 to the right, it's equal to the sine function. Now, we don't have to shift the cosine function to make it line up with the sine function. I could shift the sine function to make it line up with the cosine function. So to do that, I could shift the sine function, the green one, pi over 2 to the left, and then it would line up with the cosine function exactly. So let me do that. There we go. Notice once again, they're the exact same function. So that's what this says here. Because of their periodic nature, there are many equivalent trig expressions. Horizontal translations of pi over 2 that involve both the sine and cosine function can be used to obtain two equivalent functions with the same graph. Translating the cosine function, pi over 2 to the right, so by doing that transformation, making the d value pi over 2, so cos of x minus pi over 2 is a cosine function that's been shifted pi over 2 to the right. That results in the exact same graph as sine x. And just like I showed, we could instead transform the sine function pi over 2 to the left. By making that equation, sine of x plus pi over 2, that makes the d value negative pi over 2, it shifts it left pi over 2. That would give us an equivalent function to cos x. So our two identities, a cos function shifted pi over 2 to the right is equal to a sine function, and a sine function shifted pi over 2 to the left equals a cosine function. So those are the transformation identities. Next identities I need to remind you about are the even and odd function identities. So we already know about identities for even and odd functions, right? If we have even functions, we know f at x equals f at negative x, and they're symmetrical about the y-axis. And if we have odd functions, we know that negative f at x equals f at negative x, and they have rotational symmetry at the origin. Let's apply that to trigonometric functions, sine, cos, and tan. Let's look at the graph of cosine. Notice that graph is symmetrical about the y-axis. If we did cosine of 2 pi and cosine of negative 2 pi, they would have the same y value. Their y values would be at 1. And that's true for any angle you plug in. Let me show you. Here's the graph of cosine. If I plugged in 3 for x or negative 3 for x, it should be the exact same thing. Because if we notice, if I were to plot the points for when x is 3 and when x is negative 3, if we look at those points, notice they have the exact same y value. And that'd be true for any x value I picked. So let's say I picked 5. That means that if I were to also pick an x value of negative 5, the points would be at the exact same y value. And notice that they are. The y values are both 0.284. So here it says cosine is an even function, reflecting its graph across the y-axis results in two equivalent functions with the same graph. What about sine x and tan x though? So let me change this to sine x. If I evaluated sine x at pi over 2, I get 1. But what do I get if I were to evaluate it at negative pi over 2? So f at negative pi over 2. Notice I get negative 1. Same absolute value, but opposite sign. Maybe that's a coincidence. Maybe that's just for pi over 2. Let's try like pi over 6 and negative pi over 6. Once again, same absolute value answer, but opposite signs. So our general conclusion would be that if I multiplied sine x by negative 1, it would be equal to sine of negative x, right? If I were to multiply sine x by negative 1, notice now it's equal to sine of negative x. And tan is actually the exact same. It's also an odd function. So we say they have rotational symmetry about the origin, and our general conclusion for the identities would be, well, since cosine is even, cos of negative x is equal to cos of x. But sine and tan are odd functions, which means that sine of negative x is equal to negative sine x, and tan of negative x equals negative tan x. So we'll need these identities as we move forward as well. The last new identity I want to show you for today is what's called the cofunction identity. And what that does is it describes the relationship between complementary angles in a right triangle. So if we have a right angle triangle with some reference angle theta, I know the other angle could be calculated by doing 90 minus theta, or in radians, pi over 2 minus theta, right? Because the angles in a triangle have to add to 180, and we already have a right angle, I know that the other two angles would have to be complementary, meaning they add to pi over 2 radians, or 90 degrees. So for example, let's make this easy. If we were in degrees, and I knew that this was 20 degrees, that would mean this one down here would have to be 70 degrees. I can get it by doing 90 minus 20. So I think you get how that works. Now, if you remember SOHCAHTOA, let me just write it at the top. Depending which of these two angles, this one or this one, we made our reference angle, we could come up with some equivalent expressions for ratios of sides. Like, for example, if I were to do sine from theta, it would be this side over this side, opposite over hypotenuse. Now, that's not the only way I could create a ratio between those two sides in this triangle. I could also do cosine from that angle. Cosine from that angle would give me the same two sides. It would be adjacent over hypotenuse. So what I could say is sine of theta is equal to cosine of pi over 2 minus theta. Or in this case, I've replaced theta with x, but same thing. Right, this identity says sine from here equals this side over this side. And cosine from here equals the same ratio, that side over that side. So they must be equivalent. That's an identity. Another way we could think of the same thing would be to do cosine from here would be that side over that side, the same way that sine from here would be that side over that side. And that's what's written here. Cosine of angle x would be equal to sine of pi over 2 minus x. So basically, and I'll put this in, I think it'll be easier for you to think of this in degree mode for now. Basically, all I'm showing you is that sine of any angle would be equal to cosine of its complementary angle, meaning the angle that would make 20 add up to 90, which would be 70. So notice sine of 20 and cos of 70 are equal. Or cos of 10 and sine of 80 would be equal because those are complementary angles. So it wouldn't matter in the triangle whether you were doing cosine from the 10 degree angle or sine from the 80 degree angle, you'd be doing the same ratio of the same two sides. Now, of course, we're not working in degrees, we're working in radians, but I find people often understand it better when we talk in degrees. Oh, and one more thing, I mean, we can extend our understanding of what I just showed you and our understanding of the cast rule to come up with a few more identities. So we could identify other equivalent trig expressions by comparing principal angles drawn in standard position in quadrants 2, 3, and 4 with their related acute or reference angle that is in quadrant 1. So for example, if I have some angle x, that when I do pi minus that angle x, I'm in quadrant 2. So let me just draw that for you. So if I'm in quadrant 2, that means I'm here, and here's pi, and the reference angle is x. And that means this entire principal angle is pi minus x. If I wanted to calculate sine of the principal angle pi minus x, based on cast rule, I know it's going to be equivalent to sine of the reference angle. So I could say sine of pi minus x is equal to sine x. But what if angle x, the reference angle, brings us into quadrant 3? If it brings us into quadrant 3, that means I am here, the reference angle is x, the principal angle is the angle pi plus x. Based on cast rule, I know I could get the ratio for the principal angle, sine pi plus x, by doing negative sine of the reference angle, because I know in quadrant 3 only tan is positive. So I could say sine of pi plus x equals negative sine of x. And same thing in quadrant 4. Notice in quadrant 4, if we were in quadrant 4, sine would be negative there as well. So if I wanted sine of 2 pi minus x, which would be an angle in quadrant 4, the principal angle is 2 pi minus x, reference angle x, I could use sine of the reference angle as long as I make it negative. So there's just a few more identities that you already knew how to create, we just maybe hadn't given them names before. Okay, we just came up with this cofunction identity. Pi over 2 minus x and x are complementary angles. They would add to pi over 2. So we know that their cosine and sine ratios are equal to each other. I'm going to prove this to you, not geometrically like I did over here, but I'm going to prove it to you algebraically going through a proof using the transformation identity. So I'll separate into left side, right side. If I want to prove that the left side equals the right side, I can use any other identity I know to do that. So I'll use the transformation identity, and to use that, I'm going to first rewrite the order of the subtraction that's happening here. Instead of pi over 2 minus x, I'm going to rewrite the negative x term first. So I'm going to rewrite it as negative x plus pi over 2. That's the same thing, equivalent to what I wrote above. And now I'm going to common factor out a negative 1 from both terms, and I get x minus pi over 2. And if you remember, cosine is an even function. Cosine of negative of an angle is equal to cosine of the positive of that angle. So I could replace that with just cosine of x minus pi over 2. And cosine of x minus pi over 2, well, a cosine function shifted pi over 2 to the right is equal to a sine function. So I've just proved the identity using the transformation identity and the even identity for cosine. So I was able to go from here to here because I know cosine is an even function, and here to here based on the transformation identity. We can see left side equals right side. Okay, let's prove the other cofunction identity. It's the same thing. These two angles are complementary, so I know sine of one of them is equal to cosine of the other. I'll separate into left side, right side. How I'm going to do this one may seem a little counterintuitive at first, but I'm actually going to make the right side look like the left side. And how I'm going to do that? Well, I know cosine is even, so I could say cos x is equal to cos of negative x. And I can rewrite any cosine function as a sine function as long as I shift it pi over 2 to the left. So I could rewrite this cos of negative x as a sine of negative x as long as I shift that pi over 2 to the left. That's the transformation identity. And then notice all I have to do is rewrite the order of those two terms that are in the argument of sine. So instead of negative x plus pi over 2, I could write it as pi over 2 minus x. And that's the exact same as the left side. So we've proven that one as well. Left side equals right side. And I did that by first using the fact that cosine is even, and then using the transformation identity, and then just rewriting the order of the terms. This last example is just kind of going to be a way that we can apply the cofunction identity. Given that sine of pi over 5 equals this approximate value, let's use equivalent trig expressions to evaluate cosine of 3 pi over 10. Well, I know I'm going to be able to use the cofunction identity because I know 3 pi over 10 and pi over 5. I know those are complementary angles. How do I know that? Well, 3 pi over 10 plus pi over 5, right? Pi over 5 is 2 pi over 10. That gives me 5 pi over 10, which is pi over 2 radians, which is 90 degrees. So when two angles add to 90 degrees, I know they're complementary, which tells me that sine of one of the angles is equal to cosine of its complementary angle. So I know this expression is going to have the exact same ratio. But let me just communicate that in my answer here. So cosine of any angle is equal to sine of pi over 2 minus that angle. That's the cofunction identity. And then if I simplify in the brackets, pi over 2, let's rewrite that with a common denominator. So that would be 5 pi over 10 minus 3 pi over 10, which is 2 pi over 10, which is, of course, just pi over 5. So what I've just shown in these few steps here is that cos of 3 pi over 10 is equal to sine of pi over 5. And the question tells us sine of pi over 5 is about 0.5878. So I could say it's about 0.5878. Cos of 7 pi over 10. So once again, I don't want to use a calculator to get an approximate value for this. I want to use this information to be able to figure out an approximate value for that. I only know information about a sine function, so I can rewrite this cosine function as a sine function using the cofunction identity. If I want cosine from 7 pi over 10, I could do sine from its complementary angle. So sine from pi over 2 minus 7 pi over 10. And then I'll simplify this and see if this helps. Pi over 2, I'll rewrite that as 5 pi over 10. So I get sine of negative 2 pi over 10, which is sine of negative pi over 5. Oh, and I know sine is an odd function, so I could rewrite this as negative of sine of pi over 5. And we know from the question that an approximate value for sine pi over 5 is 0.5878, so this is about negative 0.5878. 7/8. So that's just a little example of how we could use the cofunction identity. All right, that's it for this lesson. That's a good intro into how we're going to be working with identities in this course. And hopefully you're able to see how we can use the transformation, cofunction, and even odd identities moving forward.